welcome to lecture number 28, and as you know we have been discussing how to analyze circuits using Phasor notations, and in fact by Phasor analysis, if you solve a circuit which is only applicable for excitation which is sinusoidal in nature, and the solution that you will get here will be the solution due to forcing function alone, because transients will be born, they will die after some time depending upon the time constant of the circuit, how long it will last, that transient, that is decided, but in any way for all practical purposes they will eventually die down, and only the solution due to forcing function is of concern after certain time, after you have switched on the circuit, and then steady state condition prevails, and that steady state solution is nothing but the solution due to forcing function that we have seen earlier. So, here is a technique which will allow you to solve for the forcing function solution rather easily by using Phasor approach. So, we have seen, for example, if it is an RL circuit, I will just briefly summarize. Suppose this is the circuit RL and this is the current I want to find out, when the excitation is Vm, suppose sin omega t, and the corresponding current is I t. This is everything in time domain, and I know how to solve it. If I know the initial current etc., I will be able to solve this, and this current will have I n t and I s t or I f t. Now, this circuit you redraw when you draw the Phasor analysis, R remains R here, but this inductance you replace by j omega L, and this voltage I will write it as, time will not be present now, will not be present. So, this V t is this V bar, which will have a magnitude and angle, and I wrote it as V max it will be, and similarly the current phasor will be I bar. Okay. And I bar will be I angle minus theta. These are essentially, it is nothing but V m e to the power j 0. In short, instead of writing e so many times, you put the angle, that is good enough. So, this is your current, and this two together R plus j omega L is your Z, complex impedance. Complex numbers, it is a constant number, property of the circuit. Only thing it takes from the supply is the supply frequency, which is constant. Therefore, this is also, so it will have a magnitude as well as an angle z theta. And we have shown you that I bar is nothing but V bar by I bar, no differential equation, and this is V m 0 and this is z theta, and it will become equal to V m by z, magnitude without bar and angle minus theta, e to the power j 0, below it is e to the power j theta, e to the power j 0 minus theta, that is why minus theta. So, this will be the current, and of course, after you get this current, to write the in the time domain, it will be I t will be if this is the phasor form, I will say, oh, the current value is V m by Z into sine of omega t, but it is lagging minus theta. So, I can switch over from time domain to frequency domain. This is called frequency domain or phasor approach in no time. That is how the circuit is solved. Therefore, wherever inductance is there, you write it as j omega L. Similarly, for RC circuit, for example, R and a capacitance, this is in time domain, in this column time domain, which is where everything is real. This is R, this is C, and here is some voltage applied, which is of course sinusoidal. V t is equal to V m sin omega t. Okay. And this current I t is steady state current. We will not carry on that I f t or I s t, because we understand with respect to the context we are telling. We are only interested in steady state current. This is same as your I s s t, or which is same as I f t, solution due to forcing function. These are all same. So, I will write henceforth as I t. So, with respect to context, you have to understand. Here also there will be some time domain current if you apply such a voltage, and in time domain we have solved this earlier, and the solution for the current was shown to be V m by Z into sine of, this time it will be omega t plus theta, where tan theta is equal to 1 over omega c over r, that is 1 over omega c r. Similarly, here it was tan theta was omega L by r. Okay. This omega L is called omega L is called the its a dimension should be ohm, because after all current is amperes, voltage is in volts. So, omega L will be in ohm, and it is called reactance. R is resistance, omega L is reactance. Not only reactant, it is called inductive reactance, because L is involved, inductive reactance. Similarly, here it will be like this. So, this is known without knowing phasor diagram. I knew this. Then once again you can draw the circuit in terms of phasors as R, then capacitance, everything I will now convert to phasors, plus, minus, polarities are maintained. So, R will remain R, and this is actually minus j x c, which is equal to minus j over omega c, because from this I know this. What is z here? Z here will be equal to r square plus 1 over omega square c square. So, 1 over omega c is of dimension in ohm, and it is called capacitive reactance, Okay. And then in this circuit from time domain, I should not write now small letter V bar is the applied voltage, phasor, current phasor is I bar. There will be no time involved here, and only thing is this Z bar here will be equal to series. So, R minus j by 1 over omega c, which will have a magnitude of r square plus, you know this, but once again quickly reviewing, and this angle is minus theta. Okay. So, that current will then become V bar if this voltage is V m 0 degree. So, write V m 0 degree, V bar by Z bar. Z bar is this one, which is equal to magnitude of Z bar minus theta, and Z is this one. So, Z. So, while dividing and multiplying phasors, it is better you express in polar form, and while you want to add complex numbers, it is always better you express it in rectangular form. Addition, subtraction of phasors can be easily done if it is expressed in rectangular form, a plus j b form, and division, multiplication better use it. But in nowadays the scientific calculators will have all the provisions, you can mix up, multiply a complex number which is expressed in polar form, and another is in rectangular form, a plus j b form, multiply them, they will give you result. You can easily switch over from polar to rectangular wherever you want. Polar form is always better in the sense that it gives you the magnitude of the phasor as well as its phase relationship with respect to reference phasors. So, anyway, so this is equal to your I m and this is minus theta. So, this will become plus theta. So, you see the current will then be leading the supply voltage. If it is RC circuit, I am not writing any more things about it, you know a bit of it quite good in your first year circuit analysis. But the point to be emphasized is that because of this relationship, that V bar equal to I bar into Z bar, it is tremendous, this relationship. It is similar to V equal to I R in your DC circuit. Therefore, series parallel of impedances, division of current in two impedances, all the formulas that we used for DC values is also applicable here. Only thing to remember that these are no longer real numbers, real constant numbers, but they are maybe complex numbers. That is all. No solution of differential equation now, if the excitation is sinusoidal in nature. Got the point. So, there may be, for I showed you last time, which I am not doing, for example, two impedances connected in series, just add them, get the total impedance, supply voltage divided by the total impedance will give you the current. Similarly, two impedances are connected in parallel, current in one branch I 1 will be total current into Z 2 divided by Z 1 plus Z 2, and so on. All the things that we learned in DC circuit will be applicable also here. Star delta conversion of resistances connected can also be applied to star delta conversion in impedances. But what I am telling, you should not be under the impression I am doing this thing V t by I t. It has got really no sense as such. At every instant it is varying. What we are doing? We are changing these voltages in phasor forms, then playing with them where the equations will be only algebraic, no differential equation. Then if I wish, I will be always able to come back to the time domain in no time. That is the idea. For example, if I say, giving you some example, suppose I say there are two voltage sources in time domain first I am doing, it is given as V 1 t and another sources which is with the polarities are important mind you, this is V 2 t and both are sinusoidal. Okay. And this is A, this is B. So, suppose let V 1 t be is equal to B maximum 1 sin omega t plus pi by 6. Suppose somebody says sinusoidal voltage and V 2 t is equal to, somebody says V 2 t is V m 2 its maximum voltage into cos omega t. Now, here you should be a bit careful because sine cosine terms are involved. In Phasor notations, always try to express them either in sine or cos, both of them, all the quantities in the same reference frame you bring. For example, I will write it this way, B m 2 cosine omega t is what? Cosine 90 minus theta, this way I can write, is not? So, you have to bring it to same quantity, that is sine. Suppose this quantity is sine, this is also like this sine 90 minus omega t and cosine is a very nice function. So, this is nothing but sine, oh no. So, cosine 90 minus theta. Now, this can be written as sine then omega t minus 90 degree, then sine will come because sine theta is equal to sine minus theta, sine minus alpha is equal to minus sine alpha, we know this. So, I will write first transform this one, this is V 1, I have not disturbed that, and V t 2 I found it was given in cosine. So, I brought it to sine level and I will write it like this. Got the point? V m 2. So, this is V t 2. Okay. Then you see I will then write V 1 t which was V m 1 sin omega t plus pi by 6, I was writing like this, it was given. So, this I will write it as phasor, its amplitude V m 1 and associated angle. Now, this phasor is leading sin omega t by 30 degree. So, I will write plus 30 degree, is not? Plus means leading. Now, this V t 2 t I am writing as minus of, let me write like this, there is a minus sign. So, minus sign I will keep it and its phasor is V m 2 and angle is minus pi by 2 means e to the power this thing. Now, if you are asked to what is the problem here, suppose two sources which are sinusoidal in nature, they are connected in series with this polarity, you have been asked to calculate what will be V a b t. So, I am taking help of phasor notations to calculate it rather easily. In time domain also I could do it, what you have to do? So, V a b t in time domain, if you want to do it, what will be your sequence of steps? It will be this plus V m 2 cosine omega t. then I am not doing this, but what I will be doing then? I will break this sin omega t cos plus cos sin, and then I will group sin terms together, cosine terms together, multiply by coefficients root over coefficients of sine terms and cosine terms, divide it, then you will be able to express in the form of some sin omega t. Everything I can do remaining in time domain, but the steps involved will be a bit more compared to the way I am doing now using Phasors. Same problem I am now going to solve. So, what I have done? I have written, I should not write equal to, this is my V 1 bar, this Phasor, and this one is V 2 Phasor is equal to minus V m 2 and angle minus pi by 2, like this I have got. Generally Phasors this minus sign, it should have a magnitude, polar form it is. You can leave it with it, or you can sometimes write this as any Phasors, as I told you, can be shown by a line, say V m 2 magnitude, this is minus pi by 2, wherever it will be with respect to reference. Negative of any Phasor is this one, rotation of the Phasor by an angle of pi by 2. Therefore, you could also write it. So, these are small tricks, not tricks, but you should be careful what is. So, you can leave it with it, or you can also write it as okay, let us first leave it. So, this is V 2 bar, let me say V 2 bar is this Phasor. Let us not complicate the issue further. So, this is the Phasor, this is one Phasor I can draw, magnitude and angle, then negative of that is what I am telling. Now, VABT can be done like this. Now, I will do in this way. In Phasors, I will say potential of A with respect to B, no time I will show, and this will be equal to minus to plus. So, this is equal to your V 1 bar and this is equal to V 2 bar, with plus minus remains as it is. Therefore, your potential of A with respect to B, just like DC circuit here, minus to plus B 1 bar plus minus to plus V 2 bar. You have to add these two voltage Phasors, and what is this one? This one is V m 1 plus pi by 6, and what is this one? V 2 bar is minus V m 2 minus pi by 2. Got the point? Add this using your calculator, two complex numbers you get. Ultimately, you will be getting some V m and some angle here. I am not doing that, but some angle you will get, say theta dashed. And after you get this, then you will say okay, resultant voltage across A B in time domain V A B T will be this V m, whatever it comes, this V m. And since I have expressed everything in sine, so with respect to sine you will get this angle. If it is plus, write plus theta dashed, if it is minus, write minus theta dashed. Therefore, not only differential equations can be substituted by algebraic equation with complex numbers, but addition, subtractions of complex numbers, also sinusoidally varying time domain functions can be very easily done transforming each of those quantities in terms of phasors, and you will get the answer. Okay. So, this is in nutshell you solve it. But one thing I will give you several problems on this, to that is, if the Phasor notation is known, what is the corresponding time domain expression, okay, and so on. Now, I am going to tell you about the power in such circuits which are excited by AC source. This is important as well as very interesting to know that. In case of DC circuit, because in this in case of DC circuit only resistance is there, power supplied by the source will be always consumed by the resistance and nothing will be returned back to the supply. Whatever power goes to resistance, it is lost forever. But since in AC circuit there will be R, L, C all are involved as circuit parameters, then the current waveform may not be in phase with the voltage waveform, there will be a displacement, there will be instants at which current will be power will be delivered to the circuit, there will be instants when power will be returned back to the circuit. So, in which way that goes on I will tell, and for that I will remain in time domain. So, instantaneous concept of power in AC circuit, power in, people call it AC circuit, AC circuit. AC circuit underlying that AC means sinusoidal AC, sinusoidal. It has become synonymous. AC means sinusoidal voltage. In our country or elsewhere, power is generated at sinusoidal AC voltage waveform and that is being used. So, let us see very carefully. For example, you have a circuit like this RL and in time domain I am here. This is your supply voltage V t is equal to say V max sin omega t, and the current is I t, and I am interested only in steady state current as I told you. So, I will go to complex plane, solve for current phasor, then I have come back to I t, and this current will be V max, we know that, divided by Z into sin omega t minus theta. This V max is only the magnitude of this Z. What is this Z? Z complex number is R plus j omega L, and magnitude of Z bar, which I will simply write Z, is this one, R square plus omega square L square. So, here nothing is phasor, so in time domain I have got it. Now, look at the direction of the current and polarity of the voltage that I have indicated here. And we know that this source, this is the supply, is current is flowing out from the positive of the supply. Therefore, power delivered. So, with this polarity I will only write in language as power delivered by the source, instantaneous power delivered, instantaneous power delivered to the source. No, power delivered by the source, power delivered by the source to the these two are load R and L, this is load to the load, this is the thing, or to the circuit it is delivering power. How much it is? Instantaneous power. So, it will be V t into I t. Okay, if this product comes out to be negative and you are telling instantaneous power delivered to the by the source to the load, that will be actually in the opposite way current is coming. Got the point? This is very important, V t. Now, let us put this magnitude here, and this V max by Z I will write it as I max. So, I will multiply V max, I will put these values sin omega t into I max sin of omega t minus theta, which is equal to V max I max into sin omega t into sin omega t minus theta. You see, you are multiplying two sine terms, sine can vary, it can have magnitude between -1 to +1, both this term and that will not occur simultaneously. So, sometimes this product will be positive, indicating that at that instant power is absorbed by the circuit. Sometimes this quantity may become negative, that means it will be pumping power back to the source. So, this is source. Okay. Acha, let us just this much I will tell right now. Suppose I sketch it in time domain, this is omega t, okay. Omega is constant and I sketch here, I would like to sketch here P t. Now, how can I sketch it? I will first sketch the supply voltage, this is your this V max sin omega t, and then I will sketch I t. I t RL circuit, it will lag by some angle theta, value of theta may be 0 to 90 degree only. So, current will be lagging like this, steady state current. It was there, here also it is there. Anyway, and this angle is theta, this angle is theta. Whatever happening to the voltage waveform, that is 0 going towards positive. Similarly, this point current 0 going towards positive will happen after theta. Similarly, this theta will be between peak to peak also. You know this. So, this is the thing. Now, you look then below, this is voltage, this is your voltage and this is the current I t, is not. So, this power, instantaneous power. So, this side is corrected V t and I t I have sketched. This is I t, this is V t. What is I t? I t is equal to I max sin omega t minus theta. Now, you see below this I will sketch the instantaneous power. What is that? Product of at any instant I will multiply voltage and the corresponding current. At every instant I will go on doing like that and sketch it here. Now, you see you first break up this thing wherever voltage has got a 0 crossing and current has got a 0 crossing, changing from plus to minus like that. And let us divide this interval. Got the point? So, what I have done? Voltage waveform was there, 0 crossing, I have marked with bullets. Similarly, currents wherever 0 crossing, I have marked up with the bullets. Now, during this interval, voltage is plus and IT is negative. So, actually current is flowing like this and this is plus. So, supply is absorbing power, got the point? And this product will be negative. Use a different color for that. So, this product will be this, during this to this voltage is plus and current is minus, something of this sort will happen. At this point once again it will be 0. Now, during this interval, this to this, both voltage and current is positive. That means it will be something like this. At this point once again it will be 0, but power will be positive. Really voltage is positive in real terms at that during this instant, any time you choose, voltage will be positive, means this is really plus, this is minus, current is really positive. So, it is flowing this way only. Therefore, I will conclude it is delivering power here, power delivered. And during this zone, power delivered I have calculated and which has come out to be negative. So, I will say it is absorbing power, source is absorbing power. During this zone, you see once again current is plus, but voltage is minus. Therefore, polarity will be such that it is pumping back power back to the supply. And here in this zone, both voltage and current in this time interval, both voltage and current has reversed. So, once again it will deliver power, product will be plus. So, it will be like this and so on. Therefore, you see as a function of time, the instantaneous power delivered by the source to the load looks like this, with the positive side more. Average value of this is not 0. It is not a sine wave like this, equal excursion on the plus and minus sign. It is the positive side will be more interval, more values like that. Therefore, during this time power is delivered and during this time power is absorbed. Got the point? And this gives you a fair, because after all there is resistance. So, some average power must exist. Therefore, people say that the average this waveform PT, this average power of this waveform, blue colored waveform, which shows the instantaneous power, will be positive, indicating that the circuit on average absorbs power because of the presence of the resistance there, because the power will be lost there. So, we will continue with this in my next lecture. Please go through it carefully. Thank you.